Turns up 5 days late, but I can assure you I've been working. In the background, helping organize these things. It's just that a lot of teaching is going on, so I've not been on campus. I've been in the main campus where I've been teaching. Uh, I'm not going to spend too much time introducing myself, but before I introduce the speaker, I've been asked to make an announcement. So today was supposed to be group discussions, right? Tomorrow again, there are group discussions. I don't think you need to record this. You're recording all this? Okay, good. Yeah. So if you're not planning to come, please inform Mr. Naveen. Okay, because a lot of food is going to get wasted if you're not coming. Hmm? It's okay. You can form your groups and you can do your group business anywhere, but just inform us so that we know how many people are coming here for lunch. Now I'd like to introduce today's speaker, Praveen Karant. He is from the Center for Ecological Sciences. He is an associate professor there. He's been there for the last 10 years. And he is one of the pioneers in India doing molecular phylogenetics, biogeography, and in fact, one of the pioneers in evolutionary biology in a sense. And he's been, his main interests are phylogenetics, biogeography, and species delimitation more recently. He's been working on quite a lot of different taxa, including reptiles, plants, and amphibians, uh, butterflies. Yeah, he's been a collaborator with me. I work on butterflies, by the way. So, yeah, today he's going to talk about some of the things he's been interested in. A little bit of this will be a repetition of what you already discussed with Mike Arnold, but I'm sure it'll be a good refresher for you, and also you will hear about the same things but from a different perspective, right? So as usual, I'm sure you'll all be very interactive, discuss a lot, and let's all have fun.
Okay, thanks, Ulasa. It's always fun to be back here. And what I'm going to discuss here today with you will enthuse you to do some of the similar kinds of studies on systems that you're working on, or at least um, expose you to some of the um, patterns that we have been ignoring for a long time. Okay. Now, Mike Arnold has already covered some of this material. Um, you'll sort of realize that as we go along, but then we're going to give it a slightly different twist. Okay. So let's start with this simple question. By now, you should know the answer. So, what is a species? What in your mind is a species? That's a question to you. So we are not going to move from this slide until I get at least a couple of answers. What's a species? Are we humans a species? Yes? Okay. How do you define a species? Lorenzo, you don't get to answer. Come on, let's hear it.
Before this workshop,
Huh.
I used to believe in that biological speciation
are really confused as to what is a species, right? So which is the most widely accepted concept? You already mentioned it, the biological species concept, right? Which basically says species are entities that are reproductively isolated from other such entities. Everyone is hybridizing, having a gala time. So what is a species, right? Um, but do we need to really define something called a species? Is it necessary to do that? Or to better understand biological systems, it's nice to sort of put it in a pigeonhole and say, okay, all these entities share a certain character, they're a species, and then we can go on to study them, right? And then look at diversity of life and all that. So it is an important endeavor. So biological species concept. So that's what people have been following for the longest time, right? What are the problems with biological species concept?
That can be used for those organisms who reproduce asexually.
It cannot be used for defining, delimiting species in organisms that reproduce asexually.
Okay, no.
It's okay.
Praveen,
Can you hear me?
it's fine. Actually, recording is up.
Oh, for recording. Okay, sorry. Okay. Oh, I hate these mics. Yeah, fine. All right. Okay. Where were we? Yeah. So one is asexually reproducing organisms. But we'll come to that in a minute. And the other one is hybridization. Yeah, if there's hybridization going on, then if you're using it, it should not be happening. Either you subsume both of those species into one species, right? Or you come up with another definition of what a species is, right? Excellent. So those are definitely two, some of the issues with biological species concept. So we already know what biological species concept says. The main thing is reproductive isolation, right? And there are all these isolation mechanisms. I'm sure you've already gone through it, and then you guys already spoke about these two major issues, right? And of course, this is not a major issue, but in case of fossils, you don't know what's really going on. You can't really test if those fossils were hybridizing or not, right? But you're right. These are the two main reasons why biological species concept is problematic. But I would argue that it's actually down to just that. Asexual species, why do you think is it really asexual? Exactly, they don't have sex in the conventional way that we understand, right? But they are exchanging genetic material, right? So it's actually hybridization, and Michael Arnold has been talking about it a lot. All right, now, so we have this idea of a species, and these are entities that are reproductively isolated from other such groups. Now let me ask you something. Now this is the definition of species, but when we are actually describing a species, do we test for reproductive isolation? These are assumptions. Major cases, and in fact I would say in most cases, these are almost never tested. Right, but how do you describe a new species? They look different, okay, something that looks different, and you find something very different from what's usually found there, and you're like, this might be a new species. And then there's another term you use, threshold, right? So the question is, how different should something be before you call it a different species, right? So we'll come to that issue also in a bit. So we are defining, or we are describing species, we are delimiting species based on morphological characters, right? We are not testing to see if they are reproductively isolated or not. Even though in our mind, a species is an entity that is reproductively isolated, but we never test it. Every new species description is based on morphology. But one can argue,
Can be any phenotype.
yeah, it's usually any phenotype.
I heard it from you, the
Huh.
talk that you only gave,
Yeah,
where phenotypic.
it can be any phenotypic trait, right? But can one argue that, yeah, sorry.
We usually describe a species only when we say new species.
Huh.
We usually take some traits into account which are actually species specific, for example, like genetic areas.
Huh.
So isn't this one of the good major like
Genital morphology, right? And genital morphology is, directly related to reproduction, right? So if you have entities that have a very different genital morphology, you know that these two cannot hybridize, so there must be two different species. You're absolutely right, but yeah.
Then again, that same model is based on assumption of that we have lock and key model of
Yeah. Lock and key model of?
that male and female, they are generalized, they properly fit, and if it is not compatible, they cannot be.
They probably cannot mate, yeah. But then again, no one has tested it. Yes. Huh.
and actually lock and key model is like a very good hypothesis in that sense. There are like different hypotheses now been put up in the last 6 months. That basically is like cryptic image of
Character. Wouldn't you agree? Yeah. However, if you look at new species descriptions, it is not based on reproductive traits at all, most of them. Right? In many species of insects, yeah, people do use it, but birds, mammals, birds is usually plumage, right? So most of these traits are not directly related to reproduction, right? So they don't really tell us anything about whether that entity, that set of individuals that show a certain phenotypic trait are actually reproductively isolated from other such entities, right? Does that make sense, everyone? Yeah?
Since you mentioned bird, in
Huh.
many birds there are descriptions where there is very slight change in some plumage and people are trying to describe the new species.
New species, yes. In fact, warblers, those little ones, many of the migratory warblers, which will start arriving in a couple of months, you have just one little stripe on the wing, and it's a different species, right? Yeah, Philoscopus warblers, and if you look at two of them, even a trained eye, if you have it in your hand, you can't make out the difference, and apparently they are two different species. Okay, but we'll come to that in a minute. So again, going back to threshold that you were talking about, in some cases, sister species are very, very different from each other. Morphologically, they look very different. In other cases, they look very, very similar, right? So then there is a problem of threshold. Or rather, threshold is problematic. Can we really use a threshold to say that, if I see 20% difference between these two populations, I'm going to call them two different species. Less than 20% is the same species, or less than 5% is the same species. Can we use threshold?
Isn't that molecular experience?
No, forget about molecular data now. I'm just talking about morphological traits here. Right, Philoscopus warblers, two different species, the only difference is one little stripe. There are other species pairs, closely related species pair, they look very different. Huh? Should be genre specific. Okay, anyway, just keep that in mind. We'll come back to this issue also in a little bit. Okay, now, what was it? As I was saying, now I forget where I was trying to go with this. There was something else. Okay, what were we discussing before this? Okay, it'll come back to me, that's fine. All right, so biological species concept is problematic. So we already discussed this. Most of the species descriptions are based on morphology, and morphological divergence is taken as a surrogate for reproductive isolation often, right? However, if those traits are not directly related with reproduction, this also becomes problematic. Maybe it's just intraspecific variation in morphology, maybe plumage color variation within a species, right? If you look at domestic, in the dog family, the domesticated dogs, what a variation you see, right? They're not different species. Now the other problem, of course, with biological species concept is that, hybridization, we already talked about it, especially in situations where you have species that have been geographically separated. Okay, and often when their ranges overlap, they hybridize. Okay, so why is it that in such situations there's hybridization?
There isn't been enough divergence for them to be just because they are being in collaboration, they will be separated for some time.
Can you be a little louder so that everyone can hear you?
So the reason that they can hybridize is when they come in contact is because they haven't had that enough divergence, whatever trait you say,
Yeah.
so that they have become geographical isolated, they have become reproductive isolated just because they have been geographically isolated for some time.
Okay, that could be one reason, yes, definitely. Not enough time has elapsed. So their genomes are still very similar and they are compatible. So when you put them together now, they can hybridize. But if the sister species pairs have diverged long time ago, so many mutations have accumulated along those two lineages, now the genomes are very different, they're not compatible. Yes, that's one possible explanation. But can we think of selection driving reproductive isolation?
Niches will still overlap.
Huh?
So because of that, they might, during mating, they might interbreed.
Huh?
And they might get an adaptive advantage. The hybrid might have an
Hybrid might have an, okay, we'll come to that point a little later. But what are the two sort of broad categories of speciation? You know, or what drives speciation? Yeah. But why is there assortative mating?
Hybrids are actually unfit, then
Huh?
assortative mating will get
No, that's later. That's much later. I'm talking about there is one species, right? That line represents one species. Now this, something happens here and two daughter species are born. What causes this split? Navindu, feel free to now jump in. Navindu did his PhD from CES, so I know him for a while. Yeah, people.
Might be because there might be new preferences that we want in one
New what?
new preferences for some traits.
Huh.
Selected.
Yeah, let's okay, that's just going too far, but let's think of very simple reasons why you can have this kind of a split. You have one, okay, let's look at it this way. You have one species distributed all over this place, right? And eventually somehow it becomes two species.
population density increases, they
Yeah.
start taking over separate niches.
Okay.
So, like for example, if there's competition, they might start shifting temporarily,
Yes.
or and so they for some they might get little bit more diurnal. Some that's like initial stuff like that.
Okay. Okay. So that falls in the realm of ecological speciation, right? So you have a population of individual, and there's some polymorphism in this population, and they are all exploiting the same resource. Okay. And obviously, if you are all exploiting the same resource, there's competition. There's competition within that species, and turns out some of these individuals are able to better exploit something slightly different, right? And then immediately you have those individuals doing better exploiting that resource, right? And then you have divergence occurring within the population, right? So species are now we call them niches. They are now there's this new lineage that is adapted to a different niche, right? So that would be ecological speciation, right? What are the other possible reasons for why this could happen? Yeah, so this would be in sympatry. That would be in sympatry. So can we think of another scenario, which is geographical isolation? Yes, yes, precisely. So you have one population. There's a barrier that comes up. Yeah, and then the population gets divided into two subpopulations, and they start accumulating changes. There is no gene flow between these two subpopulations. They start accumulating changes, right? And eventually they become two different species. So that is geographic speciation, right? And this is, broadly speaking, ecological speciation. I'm just very crudely defining these terms here, okay? And that's fine for now. But you might want to look up the precise definition of these terms in your free time. Okay, so ecological speciation, geographic speciation. Here there is a barrier which basically divides the population into subpopulations, and then there is no gene flow between those two subpopulations, and eventually you have two different species. Now, under which condition is there pressure for reproductive isolation mechanism to evolve? This is geographic speciation, this is ecological speciation. Under which condition is there a pressure for reproductive isolation mechanism to evolve? Huh? Louder. Ecological. Would you agree? Yeah? Because here, these individuals which have these advantageous allele, they want to mate with others with the same advantageous allele, because only then they can do better, right? And so within no time you have reproductive isolation arising here. Okay? But here they are separated anyway. Huh?
You mentioned within no time they become two species, but there has to be a very strong selective force for recognition. Unless that happens.
Yeah, you are absolutely right. Yes, you are absolutely right. In fact, this whole area, this is sympatric speciation, right? And it's been very, very controversial. But let's just, over here there is greater pressure so selection will drive the reproductive isolation, evolution of reproductive isolation in this case. In this case, it might be a byproduct of isolation itself, right? Because they are isolated now, there is no gene flow, their genomes are accumulating a lot of changes, they are not compatible with each other anymore, right? But there is no selection for reproductive isolation. Reproductive isolation might be a byproduct of just geographic isolation and lack of gene flow, mainly lack of gene flow. So what? It went back to this. Okay, yeah.
Okay, but for these six species,
In this case,
what is the chance of that one species will, means one population which accumulate the changes
Yeah.
will outpopulate the others or competitively exclude others?
Yeah, no, but remember here what is happening is the two species are now adapted to slightly different niches to avoid competing with each other. So what you're saying won't happen here, right? Otherwise we won't have the split at all. Yeah, both the species are now daughter species are now occupying different niches. Okay. Okay. So so this is what we mean. Geographically separated species, when you have allopatric speciation, might interbreed when in sympatry, because probably reproductive isolation has not evolved here, because there was no need for it, right? Species evolve in their own ways. I mean, we would like to believe that they should not be breeding with each other. They don't care. They're just doing their thing, right? Evolution is just doing its thing. So, so here reproductive isolation mechanism might not have evolved. They might have got separated recently. The genomes are also quite similar, but they are actually two different species. Okay, and then if you have a situation where this barrier breaks down, and where their ranges overlap, they will hybridize. Right? Does that make sense, everyone? Yeah. So that is what I mean here. When in sympatry. Okay, so then let's go back to morphological divergence. So we talked about how in some cases the sister species are very different morphologically. In other cases, you know, there's very subtle difference. Can you have a situation where they look identical morphologically? Yeah? Why not? Right? So these are called cryptic species. Okay, and we'll come back to that in a bit. So the problem, so you see the problem now? We are using morphology to identify species, to delimit species. The first problem there is, our definition is biological species concept, but morphology does not always mean that they are reproductively isolated, right? Secondly, and we are taking morphology as a surrogate for reproductive isolation, but you have cases of cryptic species. So how, you know, what is a species? How do we define species, right? So we are back to that problem. Does that make sense, people? Or did I confuse you even more? Yeah, but hopefully this will become clear in a little bit.
So why would it look different but are
Navindu, tell me, what?
The definition of cryptic species should say look identical but are reproductively isolated. It can look different.
Oh geez, okay, that's what even you pointed out. Huh? Good, you're all awake. I put in all these mistakes on purpose. Okay, it should say identical. Okay. Any other mistakes here? By the way, my spellings are terrible. I make all these mistakes all the time, so you know, feel free to point it out. Let's see. All right, so cutoff is a problem because we have something called cryptic species. In other cases, you know, sister species look very different, and there is a continuum. Okay. All right. Again, now you have all, been introduced to all of these concepts, but we have over 20 species concepts now, right? And what we are actually following is this, you know, morphological species concept. Some people say it's not a concept, or phonetic species concept. Taxonomists are basically using this fixed character difference. So if you have a population that has a fixed character difference when compared to the rest of the population, to which it looks very similar, but there is this at least one fixed character difference, a taxonomist will say this is a different species when compared to the rest, right? But basically it falls under the morpho-species concept or morphological species concept or phonetic species concept. And we have already talked about biological species concept. And there's ecological species concept, which basically says species are entities that are actually adapted to different niches, to different adaptive zones. And then there are a whole bunch of phylogeny-based species concepts. Okay, evolutionary species concept, phylogenetic species concept, genealogical species concept. I'm not going to go into the details here. I think some of these species concepts have been discussed, right? So we are back to square one. What is a species? And there are so many species concepts out there. So it was in the late 90s that Kevin DeCouras tried to sort of merge all these species concept and come up with a unified species concept. Okay, and he called it lineage species concept, but now he calls it general concept of species. But what is lineage species concept or general concept of species state, and how does it okay, sort of merge all these species concepts together? Huh? Yeah. Yeah. What is genealogy? You know what a gene is, right? If you have a collection of sequences and if you try to of a particular gene, and if you now want to find out how those different sequences of the same gene, how they are related to each other, you are basically reconstructing the genealogy. It's like a gene tree, but genealogy can also be used in terms of, you know, what's your genealogy, for example. I mean, that's also a perfectly legitimate way of using it. You know, who was your immediate ancestor, grandfather, great-grandfather, and so on. Pedigree, that's another way of looking at it. Yeah. So basically, you are tracing either an individual or a gene in a population and trying to figure out how they are all related to each other, right? So genealogical species concept, I'll come to this monophyletic part in a little bit, okay?
Even sir,
Huh.
how it is like different than phylogenetic like species concept. Like phylogenetic species concept is also it is the phylogeny is getting constructed with
Yeah,
origin.
Okay, let me spend a little time here. So here you're looking at small as diagnosable monophyletic group. Okay, does everyone understand monophyletic group? Right, so they all share a common ancestor. You know, so if you have a bunch of entities and if they all share a common ancestor, you call it a monophyletic group. They have all derived from that common ancestor. Okay, so the phylogenetic species concept is looking for such monophyletic groups, right? But it is also looking for diagnosable characters that unify them. Okay, so if you have a gene sequence, okay, so let's say these are three individuals, individual 1, 2, 3. And when you build, and let's say there are many more sequences, right? And when you build a tree, what you basically find is that individual 1, 2, and 3 branch together. So they are monophyletic, right? And there are other such monophyletic group. So that's monophyly. It's a monophyletic group, right? And there is something else which is important here. Is there a unique sequence that the three of them share? Yes, precisely. So phylogenetic species concept basically looks for the, diagnosable monophyletic group. It's basically saying what's actually uniting them is GCA. Okay, so that's phylogenetic species concept. Whereas genealogical species concept, it's just looking at gene genealogies, and it says, oh, this is monophyletic, so I'm going to call it, it's doing the same thing, but it's not really looking for these diagnosable sequences, right? And in a way, evolutionary species concept is also the same thing. So these are all the definitions. When you read them, you realize they're all saying the same thing. And eventually, they all are trying to find these monophyletic units. Okay? Yeah. No, no. It can also be morphology. In fact, fixed character differences, that is a diagnosable character that unites members together, and it says these are all monophyletic because they have the same character. There is that one character that unites them all, right? So you can use morphological characters also, Yeah.
Comparative taxonomy.
Yeah.
Earlier people have started from many authors have described different group of organisms. They have described and they have put a certain relationship among them.
Yes.
Like species, subspecies,
Yeah.
higher order.
Yeah.
And then recently we have been doing molecular biology and we are trying to understand whether they have evolutionary shift.
Uh.
So ultimately we also come up with certain relationship among them.
Yeah.
So how different, what I'm trying to ask is, how different are those earlier relationships, defined earlier relationships amongst these, like what we recover in
It varies. It varies from groups to group, and also at what level you're looking at. In some groups, it has broken down. It's like a spectacular incongruence between molecular data and morphological data. In other groups, certain places in the phylogeny there are issues, but the rest there isn't. So it really depends. I'll show you an example where, but what has happened is, and I think the example that I'll talk about in the afternoon, this will, it'll reinforce this point, and that is, often morphology-based taxonomy, you have multiple points of view. One taxonomist says this is how it should be classified. Another taxonomist says no, this is how it should be classified. Another one say another classification scheme. So often there are many different classification schemes. Okay, depending on what characters you use, how you weight them, what characters you think are important, you can have different classification schemes for the same set of organisms. Okay. In that mess, so maybe say 5 or 6 different classification schemes, in that mess might be one of them is the right one. And often molecular data helps us pick that, right? And I'll show you the example. So anyway, the short answer is it's very difficult to say 50% of taxonomy is nonsense, the other 50% is okay. It's very difficult to say that. It changes from system to system with different, at which hierarchy you're looking at, right? But as I said, there's spectacular cases. Spectacular case would be that. Do you know what these letters stand for? Okay, chimp, gorilla, orangutan, gibbon, and human. Is this the right phylogeny? What is this saying? We humans, so all of these are apes, right? So we are very different from apes. That's what this phylogeny is saying, and this is what people believed for the longest time. Where should humans fall? Over here. So apes as a group is not monophyletic. if you don't call humans also apes, right? So this is one spectacular example of that. Then you have vultures in the New World and vultures in the Old World. Turns out they are not related at all. The New World vultures actually are related to storks, and this is spectacular case of convergence. Okay, and there are also many examples where the morphology is congruent with molecular data. Okay, anyway, we have deviated here, but thanks for the question though. All right, so Kevin de Queiroz talked about lineage species concept. So he tried to unify the different species concept under one umbrella. All right, so what did he say? Okay. So de Queiroz noted that various species concepts are related to diversity of events or sub-processes that occur during speciation. Okay, and that all modern species definitions are variations of what he calls the lineage species concept. Okay, or the general concept of species. So according to him, species are segments of separately evolving metapopulation lineages. Okay, and I'll come back to this in a minute. But this first sentence of de Queiroz is very interesting. Okay, so he says various species concepts are related to diversity of events or sub-processes that occur during speciation. So when there's speciation, there's one lineage splitting into two daughter species. All these species concepts are actually talking about the sub-processes that occur during speciation. Okay, so reproductive isolation, morphological divergence, divergence in ecological space, all that is happening during speciation, and all of them actually are helping us identify separately evolving lineages, which that's what he calls a species, right? So, and he goes on to say that the gray zone is here. You know, here there's no doubt only one species, out here two species, no problem. The gray zone is here, you know, when the two daughter species have just diverged and are accumulating changes along these different axes and things are still not separated out. That is where the problem arises. And each of these species concepts are referring to the sub-processes that are occurring in that particular species pair. Okay, and this all this definition which let's not. So he says, thus under all species concepts, species are separately evolving metapopulation lineages, but under the isolation version of biological species concept, they should also be reproductively isolated. Under the ecological species concept, they should be occupying different niches. Under the phenetic species concept, they should be morphologically different. And under the phylogenetic species concept, they should be monophyletic, right? And this is an important point. The diversity of events or sub-processes that these species concepts are talking about may not occur in the same sequence when the lineages are diverging. Okay, so what I've done to make this thing, all right, so these are all the sub-processes and they refer to these species concepts right here. So sub-processes are divergence in reproductive trait, and that will result in reproductive isolation, right? And that's what we talk about in biological species concept. Molecular divergence or genetic divergence, reciprocal monophily sort of shows that, and that would be phylogenetic species concept. Morphological divergence, diagnostic characters, that's what taxonomists use. You could have behavioral divergence, you know. For example, mate recognition mechanisms might be different in the two daughter species. There's something called recognition species concept, and ecological divergence, different niches, ecological species concept. So basically what de Queiroz is saying is that when species are diverging, they are diverging along all these axes. And when you have divergence in all those axes, that's your good species. Everything is hunky-dory. But when divergence has not occurred in some of those axes, you start scratching your head and you start questioning, are they really two different species? If I use this species concept, they are two different species. But if I use the other one, they are not, because divergence has not occurred along those axes. Okay, does that make sense? Yeah. So I've drawn it up here. So you have species pair 1. First it diverges, say there's divergence in reproductive traits, then there was divergence in in the genetics, then morphological divergence, and then there was ecological divergence, and then there was behavioral divergence, say. Okay, so let's just imagine that you had a time machine, you went back in time and then looked at how that species pair evolved, and you were able to say, okay, first this happened, then this happened, then this happened. There might be another species pair where this sequence might be completely different. Is that reasonable? Right? And remember, these divergences again are driven by selection. If there is no selection for divergence along a particular axis, then you won't see divergence along that axis. Does that make sense? Yeah. So again, linear species concept, the same thing. You have divergence along different axes, and so Kevin de Queiroz basically says that presence of any one of the property or sub-process is evidence for existence of a species. Yeah. So he says, all we are looking for is separately evolving metapopulation lineages, and if one of the species concepts show them as being separate, they are separate species. Okay. Then he says more properties or more sub-processes, thus more lines of evidence, gives you greater confidence that they are indeed two different species. Huh. Yeah. He basically is saying that if any one of them has happened, they are two different species.
So basically, he is expanding conditions for defining it.
Yes.
There is one only reproductive acceleration
Yeah.
or hard line.
Yes.
Don't accept.
Yes. Now he's saying put everything in the basket. Whatever, if you see one of them, they are two different species, because that's enough evidence to tell us that these are lineages that are independently evolving of each other. Okay. Does that make sense? Yeah.
The data is
Huh.
supposed to use some supporting values like
Huh.
if only one thing is supporting that there are two different species, like this much supportive value is there, they are different species. If all are, then 100% supportive value is there that they are different species.
So then the problem is again this, right? Where along that continuum do you want to call it two different species? We again fall in the same gray area, right? Out here, absolutely no problem. Out here, it's a single species. This is where the problem arises. Depending on if you are looking at species pair 2, you will probably have only morphological divergence, and taxonomists will be very happy. And if those two species are at this stage, right? Whereas if you're looking at species pair 1, there's divergence in reproductive traits. People who would like to are in favor of biological species concept, they'll be very happy, right? But as time elapses, there'll be divergence occurring in all these axes. Okay. And Kevin is saying if you have evidence from just one, that's good enough. That is already evidence that these entities are isolated and they have independent trajectories already. Okay. But if you have evidence from more, then you have greater confidence that indeed they are two different species, right? Yeah, you had something to add? Oh, yeah, 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 of course, of course. Yes, they might. Yes, we'll come to that in a bit. Yeah,
What is the first chance of going back from true to hybridization?
yeah, yeah, precisely, yeah. Uh,
This model actually allows any process to happen. So it is actually playing in the gray area space.
huh,
If you find any one of the evidence, name them a different species.
yeah,
So
yeah. But if you can get multiple lines of evidence, it's better. So the way I look at it, look for at least 2 lines of evidence. You know, multiple, you know, at least 2. I'm uncomfortable with just one. You know,
Then why you run? Like, why
yeah,
change the next?
yeah, yeah, yeah. See, welcome to biology, everyone. Right? If you start asking such questions, that means you are a true biologist. And the answer to that question is that there is no threshold in biology.
Yeah, that is
You know,
I suppose
yes,
like to use this like in phylogeny how we use bootstrap value.
yes,
Like to indicate something like this much data has suggested they are separate species.
yes.
If we use some kind of that supporting value, that will it say the actual.
Yeah, but I'll tell you, the problem is when you're looking at, for example, uh, ideally we would like to say, okay, it is showing divergence in all 5 axes, right? I mean, these axes are also sort of, I've subsumed many species concepts into these 5 axes. If you look at cryptic species, okay, so species pair 1 here, these look identical. There has been no divergence in the morphology axis. Why? Because there is no selection for divergence along that axis, right? A good species, all of it's diverged in all the axes, so you have that problem, right? Or if you have a situation where there's a little bit of hybridization going on, but there has been divergence in all the other axes. You know, so using statistics to say that, you know, it's how do you quantify if there is significant divergence along multiple axes? You might be able to do a statistical test to figure out if there has been significant divergence along, say, one axis. But when we are using multiple lines of evidence, these are all very, very different kinds of data, right? And what do you use as your benchmark? Divergence along 5 axes, but we know in case of cryptic species, it's only 4, right? And if you have allopatric speciation, geographic speciation, reproductive isolation might not arise at all. There is no need for reproductive isolation. That does not mean they are not 2 different species, right? So there again you are down to 4, right? So that is the thing, you know, you can't really use a cutoff. End of the day, you know, it's the last few pages of a paper. You know, you read the paper. This is so typical of many biology papers. They do all kinds of analysis, Bayesian, likelihood, everything, and you don't understand any of that stuff. And then in the discussion, it's down to a verbal argument over why they think X hypothesis is correct versus hypothesis Y. Right? That's because in biology it is impossible to come up with cutoffs. In biology, 1 plus 1 is not 2. It can be anything between 1.5 to 2.5 and everything in between. It's a range. Right? So that's why Dicura said, you know, if you have evidence from one, okay, good, they are already separating, call it 2 different species. Some say, why not call it subspecies? Right? Then you need a subspecies concept, right? So call it 2 different species. If you can get more evidence, great. But I like to have at least 2 lines of evidence, you know, when you have situations like this.
In a way, it is a redefinition of what Darwin visualized as a continuum between population, maybe different populations. He did not describe the species.
Yeah, yeah.
So in a way, it seems to me like
It is a continuum. It is a continuum from individual. So the only thing definite in biology is the individual. Okay, anything above that, it's a continuum. You know.
so isn't our work model based on that idea? So we want to recognize somewhere as a mystic entity and
No, this is just a practical solution to a problem. Okay, we all understand that it's a continuum. You know, species are diverging; they might merge. How much of divergence do you really call? I mean, decide to use to call them two different species? Very iffy, very problematic situation. And there are plenty of species pairs that fall in that category. And as I said, we all recognize the fact that it's a continuum, but that does not mean that we should not try to characterize these entities as species, right? Because we need, the species is one of the fundamental units in any study, evolutionary study, ecological study. So this is sort of a practical way to sort of approach this issue. And you know, or you can also say that you need not even call it two different species. That's probably the solution to the problem. You can say these are two lineages that show divergence in this particular axis. And I'm going to go on to study them. Don't call them species. Fair enough.
naming is the taxonomic problem.
Yeah. 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 Yeah.
In case of a hybridizing species, behavioral divergence should also be absent, right? Because if they are hybridizing, they are not recognizing them as a different. The mate recognition is not working, they are not diverged, right?
Yeah. You're right, but it's a little complicated. You know, many of these hybrid zones, what's happening? So usually, a lot of this mate recognition is female mediated, right? There's a greater cost on the female. If she mates with the wrong species, you know, the offspring might not survive, or you know, might die after birth and so on. So a lot of these mate recognition mechanisms, you know, the females are the ones who they identify, say, song or dance or whatever, right? But in situations where there's hybridization happening, okay, let me give you an example. There is a hybrid zone between two species of monkeys in South India. You know, in fact, if you go up towards the Ghats from here, you have something called Nilgiri langur, and I'll talk about it later today. You have Nilgiri langur, and then once you cross the Ghats, go into Tamil Nadu, you have Hanuman langur, okay, or grey langur, and they hybridize where their ranges overlap. Okay, now there usually it is male of one species that drives away the males of other species and takes over the troop. Okay, and then they hybridize. So in this case, I don't know which one. Navendra, do you know? Is it those troops? It's the male Nilgiri langur and female Hanuman langur, or vice versa? Yeah. So usually it is the larger species, the males of the larger species. This is in the mammalian system, right? So what happens is there the mate recognition system just breaks down because it's just brute force, right? The females they have no choice there because the male has just driven away all the other males, and the females can't move from that territory because that's their home range. That's where that troop has always been residing, right? Yeah. So some of those complications happen, and you know, so those other mechanisms might not have evolved. You know.
About the entire point of for a hybridizing
Yeah.
Because see, the mate recognition mechanism doesn't necessarily need to break down
Huh.
even if they hybridize, is because whether they would mate or not is not based on evolutionary reasons, but rather on a very individual level, whether they're getting mates or not in their own population. Right. So, if, for example, if it's
Huh.
like a submissive male or say lower down the hierarchy,
Huh. Huh.
there would be a tendency for that particular individual to hybridize, but because they would have some fitness benefit instead of having zero.
Yeah. Yeah. Yeah.
So it's need not that the mate recognition mechanism breaks down as a species, but rather on an individual level, it's just to maximize.
No, I'm saying that it might not break down in this case. In some of these cases, it might not. But once you have hybrid individuals, I don't know what's happening there. You know. Yeah.
Call them a if they have.
Maybe. Yeah. Yeah.
Yeah, that's the point.
Yeah.
To answer his question, even if they do hybridize, it does not mean the mate recognition mechanism has broken down.
Yeah.
It's just
Yeah.
that those individuals are trying to maximize their fitness.
See, all individuals in the species are doing something. Then the species is doing that.
No, but not all of them would be doing.
You're just drawing a line. You're saying one individual and they say 100 or 1,000.
No, I'm not saying one in the sense that not all of them would be. Certain individuals, say in fishes, for example, they have seen that certain groups of fishes, like this, it was between Atlantic and a Pacific group, where males of one of them were more prone to hybridize with the other one, with the other species, but not the vice versa.
Yeah.
So, and they hypothesize it was probably due to more competition in this group. So that's what I'm saying. It's probably just an ecological force that was driving them to this.
The point I'm trying to make is, what is the distinction between individual driven versus species driven? Ultimately, everything is driven in terms of fitness. Evolution drives working on fitness.
Fitness. Yeah.
Evolution doesn't care about species or population.
Yeah.
Exactly. So it does not care about mate recognition. It's ultimately it has to get something or not get anything.
Yeah, yeah. So, but that's that's what I said. No, it's from a male's perspective, yes. But the female, she has to be careful, right? So, most of these mate recognition that results in behavioral divergence between species is largely driven by females. Okay, from male's perspective, you are absolutely right. The male does not care; it just wants to increase its fitness from wherever it can get. You know, it will just go for it. But anyway, let's move on here. All right. So now the question is then, how do we go about doing this? How do we identify cryptic diversity? How do we delimit those species? Because even to this day, much of the species descriptions are based on morphological characters, right? But we have a framework here. We need not use morphology, right? We can look for other lines of evidence, right? So remember, in case of cryptic species, it's a problem because they are identical. So this is what we typically do. So let's say you sample a particular species. It's widely distributed in India, and say you sequence a gene, let's say a mitochondrial gene, and when you do that, build a tree, you realize that there are actually two clades or two monophyletic groups, right? And they are geographically separated, right? So this might immediately alert you to the fact that there might be two different species that look very similar, right? Because this kind of structure, if you think about it, is also telling you that there is some barrier to gene flow. Maybe it's reproductive isolation, or maybe there is a actual physical barrier that is separating these two populations, preventing gene flow between them. Otherwise, why would you get this kind of clustering, right? So this might tell you, oh, wait a minute, these might be two different species, right? And you can actually, but you can get this kind of structure even within a population. It's called population structure, right? Because within a species, sorry. So a species is not uniformly distributed. You know, you have localized populations, right? And with little bit of gene flow between those populations. And if you do a population genetic study, you will find that, you know, indeed there's population genetic structure. That doesn't mean each of those local populations is a different species, right? So this might also be a population structure, right? So what one can do is there are actually these speciation models that one can use to figure out, is this actually population structure or is it potentially two different species, right? I'll just give you an example of that later today, but I won't be discussing speciation models per se. Anyway, so now you say, okay, you maybe use these programs to figure out if they are potentially two different species or not. Kevin DeCouras would probably say, oh yeah, that's good enough. But multiple lines of evidence is what we should look for. So then you maybe do some niche modeling, which is also called species distribution models. How many of you know of niche modeling? Have you heard that term, niche modeling? So what do you understand by niche modeling? Of a species using spatial data, right? So actually, niche modeling, I think the term is incorrect. Species distribution models is better, but basically the idea is, you know, you have those sampling locations, right? And for each of those sampling locations, you find out the various environmental parameters of that sampling location. What is the altitude? What is the rainfall? What is the temperature, right? What is maximum temperature? What is minimum temperature? All that. And then you try to find out in this landscape what are the other areas that have similar conditions, right? When you do that, you will have a better understanding of what is the environmental envelope for that species. What is the potential distribution range of that species, okay? So once you have those, you do species distribution models, and if the species distribution model also shows non-overlapping areas for these two populations, then that's an added line of evidence, suggesting that maybe on the ecological axis also they have diverged. Does that make sense? Yeah. And then maybe you can go back to morphology. Remember, these are cryptic species, but maybe you are looking at the wrong set of characters. Go back to morphology, type a whole bunch of characters, and then maybe some characters actually separate them out, but you were looking at the wrong characters, right? So use multiple lines of evidence, and then you have your species. So that's where this whole area is moving towards, and this is called integrative taxonomy, you know, because you're using multiple lines of evidence.
Why this emphasis on allopatry? Why not just take any two clades and start working with them?
Oh, okay, okay. I didn't. There was no emphasis. I just said if they are also geographically separated, then that's also one line of evidence. But you're right. You could have a situation where these two clades are in the same, are in sympatry, right? Then you go back, look at those individuals again, and see if there's divergence in other along other axes. So yeah, thanks for pointing that out. Yeah, yeah, yeah.
Is this supposed to be India, Sri Lanka? Is this familiar to me?
Did you review the paper? Hey, come on, it looks nice. You can all make out, right? I mean, this is India and Sri Lanka, it's not separated yet. Yeah, but this won't get me in trouble with the Indian government, right? This is saying Sri Lanka is part of India, so I think I'm safe. But I'm in trouble over here and over here. Okay. Questions, people?
So what's why is this not been accepted so widely, this model? Because it makes no sense when any individual species definition.
This has been, integrative taxonomy has been around for at least 2 decades now. It's just that in India we are waking up to it slowly. As usual, we are, lagging behind in so many things. This is also one of them. Sorry, you had something to say? No, the subspecies is now subsumed into species. Yeah, yeah. Because subspecies is basically already, it's just one way of looking at it is subspecies is just one line of evidence, and then species is more lines of evidence. But then again, the same problem comes up, right? If subspecies is only one line of evidence, is species 2 lines of evidence, or 3, or 4? Again, the whole cutoff business comes into play. So the subspecies is actually subsumed into this, right? So you either call them species, 2 different species, or you tell them these two, tell that these 2 lineages have diverged along this axis. That's fair enough. You don't have to name them 2 different species, nothing. You can just call them lineage 1, lineage 2, and they have diverged along this particular axis. And you can just leave it at that,
Sir, is it just the cutoff? Is it just we are in lag, as you mentioned that we are not up to it, like this method. You told like we are in lag for 20, 30 years.
Yeah. That's because we are.
I think it could be another reason that is like here there is no specific cutoff
Huh.
so that you can convince everybody. Here there are few like dimensions. Checking all the dimensions, you have to convince them. Yeah, so this is separate species or this is not. So the same convention, as there is no cutoff, you may convince yourself, but somebody else may not be convinced by this explanation.
Huh.
So maybe like that it could cause confusion between like 2 ways. That is why maybe it is not so well accepted.
No. It's not. It's mainly because we rely on morphology. We are just happy with morphology, and we completely have ignored cryptic species. It's largely because of that. Because we're just happy with morphology. And then genetic data is pouring in, and it's telling us that, look, what you're calling a single species, there's just so much deep divergence between these different clades. They must be different species. And we have been very slow in using molecular data also, right? So a combination of the 2 has resulted in this, right? And again, going back to the cutoff thing, if you think about it, if you're saying that at least one line of evidence, in a way it's a cutoff, right? You're saying there's evidence from one line of one of these lines, good enough, right? So in a way it's a cutoff, if you think about it. Yeah.
A morphological difference and it does not have a genetical difference. And if you have one and you don't have 2,
Huh.
you can get separated species.
That is an interesting point. Morphological difference and no genetic difference. Can we have that ever?
Polymorphism.
It's probably polymorphism within species.
But
Yeah.
according to this species concept, any one category can.
Yeah. Yes. So that is, again, no, that's a very important point that you have raised. So there is no divergence in the genetic axis, but morphologically they are different. So that is just polymorphism. You're probably looking at a single species, but you're right. If so, that's the thing. Morphology, again, you have to be very careful when you are describing a new species. You have to ask yourself, is this really a new species or just polymorphism within this one species? So you have to keep going back, and a lot of shoddy work has been done where those polymorphisms have been described as 2 different species. Okay, and there are some spectacular examples where males and females have been put in 2 different species. They look different. Oh, 2 different species, and So does that answer your question? So yeah, if you're using only morphology as a single line of evidence, and you're going by Kevin DeCora's statement that one line of evidence is good enough, and remember, people have always almost used only morphology, right? Then you have to be very careful. You have to look at many individuals and make sure that these are not just polymorphism within a population. With morphology, that's one thing that you have to keep in mind. Maybe even behavior things might be, there might be polymorphisms, right? Yeah, you had a.
Lack of genetic variation. So there can be epistemologic interactions that have to be addressed in terms of different levels of regulatory elements that are leading to morphological variation. So that's sort of genetic variation. You don't have variation in the sequence, but you do have in the level of transcription and translation.
Yes, yes, absolutely. Yeah, yeah. Good point. Yeah. All right. So we already talked about geographic and ecological speciation, and you guys have already discussed modes of speciation. So I think we can. The rest I'm not going to cover all this. This is all already covered, right? Allopatric speciation, sympatric speciation, and all that has been covered. So I'm just going to skip all of that. And just briefly discuss one last point and we'll break. Let's see. All right. Okay. So we talked about monophyly, right? So when you go out there, sample a whole bunch of specimens, and you're like, I think they all belong to a single species, right? And then you ask yourself, let's find out genetically, are they all clustering together, right? So that's basically monophyly, right? All of them branch together, and then you have these other species, all the entities from that other species branch together. And that condition is reciprocal monophyly. The two sister species are both monophyletic. But turns out monophyly does not happen overnight, right? So here again the cutoff threshold and all that issue comes up. So early in the speciation process, the barrier has just arose here. The two daughter species or the daughter populations will share a lot of alleles, right? So you had one population, it got divided today. Tomorrow if you sample those two populations, they will share many alleles, right? So they won't overnight become monophyletic, right? It takes time for these two daughter species to become monophyletic. So out here the condition is called polyphyletic. You have some individuals in species 1 that are more closely related to individuals in species 2 than their own individuals from their own species. Okay, but with time there's barrier to gene flow, there's interbreeding going on only within this population. Eventually all the individuals in species A are more closely related to each other when compared to individuals from species B. So during speciation, populations typically go through these various steps. First they are polyphyletic, then often it reaches a stage called paraphyly, and then monophyly. In paraphyly, one of the species is monophyletic but is nested within another species. Okay, and that's illustrated here. So that's polyphyly. Individuals here are more closely related to the other individuals. This is paraphyly. Species B is monophyletic. It has a common ancestor right here, but it is nested within species A. Give it some more time, both of them become monophyletic, and this is called reciprocal monophyly. Okay. Now, the time to reciprocal monophily is 4n generations. Okay. 4n generations. Where n is the population size. Let's say population size. It's actually effective population size, but we'll just leave it as population size. So, if the population of the new species, if you think about this, if the population of the new species is really small, it will attain monophily more rapidly, right? Because you have only few individuals that you have to mate with, and then all of you have the same genetic material, crudely speaking. But if the population size is very large, it will take longer for monophily to attain, because some individuals in that populations will still have alleles from another species. Okay. So, during speciation, this is also something that crops up. So, you might not have the species that you are looking at, if they have diverged from each other recently, they might not have attained reciprocal monophily. But they might have attained divergence in along other lines. But here, just because not enough time has elapsed, they have not yet attained reciprocal monophily. Okay? Yeah.
You mean it is actually 4 into the effective population
Yeah.
size? Is
Yeah.
the number of generations?
Number of generations, yes.
It is like a common thing.
People have done simulations to figure that out. I have no clue how they came up. Do you know how they came up with that number, 4n generation? Yeah, yeah. No, it's all based on simulation. Empirical. So actually, yeah. Actually, there might also be empirical evidence. I have not checked. There might be empirical evidence, but you know, I'm tempted. See, I'm in a diploid organism. It's 2n gene copies, right? To me, 2n makes more sense than 4n. I don't know why it's 4n. So you'll have to consult a population geneticist. Yeah.
It's like enough. I don't understand what there are two like splitting events that are taking place at the bottom.
Two splitting events.
That one, and to go a little bit about follow the middle line, and then again is that for it is right? I didn't really understand it. So
Uh-huh.
splitting into two and it's splitting into three, and then the middle one is splitting into
Oh, no, no, no. Okay. What this is these are all alleles. Look at it as alleles in the population. Sorry, yeah, I should have explained this figure better. So, these are alleles or even individuals, but let's just say alleles. Okay. So, this allele has given rise to that allele, and so on. And if it is not going any further, that means the individual who was carrying that allele died. Yeah. Okay. All right. Is that clear, everyone? Yeah. So actually, I had done some work on mole rats. Where is it gone? Ah. So this is my actually my postdoc work. So in Israel, I'd done some work on mole rats, and this particular species has 4 chromosomal. Then they used to call it chromosomal races. That's another term, right? Race, subspecies, race, and all that. Now it's been elevated to species. So you know, so there is 2n equals 52, 54, 58, and 60. So 60 is distributed south of that. 58 is here, 52 is over there, and 54 is over there. Okay, and so when we looked at and they are parapatrically distributed, slightly different climatic condition they are distributed in, and I looked at microsatellites in this species group. Now, based on earlier studies, they had done some molecular dating, and the relationship is basically 52-54 and 58-60. Okay, so that's the tree that people got. 58-60 branching together, 52 and 54 branching together, and when they did the molecular dating, turns out 52 and 54 have diverged much earlier than these two. Okay, so that is 1.6 million years ago. This is about 0.2 million years ago. Okay, so where would you expect to see reciprocal monophily? Huh? In the older species pair, right? And that's basically what we, okay, so that's 52, 54, 58, 60. That's when they diverged. And there's something else, I'll come to the monophily part in a minute. There is no hybridization between these two species, but there is hybridization going on between these two because they've just recently diverged. A pre-mating isolation mechanism is established here, but here it's not. So they have actually done mate choice experiments to figure that out. Okay, so that was all the information we had when I did this work. And then if you look at genetic divergence, there's more here, less here, and all that. This is just, it's like percent sequence divergence and all that. Now, if you look at the phylogenetic tree, on the left is microsatellite based tree, on the right is mitochondrial DNA. If you look at the northern older pair, 52 and 54, they separate out nicely. They are both monophyletic, both for microsatellite as well as mitochondrial DNA. Whereas 58 and 60, they're all mixed up, right? So reciprocal monophyly has not yet been attained. So this is, some would call it incipient species, subspecies, race, whatever. This is probably, that's the problem, when they are diverging right here, what do you call them? Right? So in this case, there is some amount of ecological divergence because 60 is found in the desert, Negev desert, whereas 58, it's more sort of Mediterranean climate. Okay, but they hybridize. So, and there's no reciprocal monophily, and they are morphologically identical. All 4 species identical. It's impossible to distinguish them by eye. Okay, that's why you use the same image. Yeah. It's actually the same exact image. It does not matter even if I put other ones. Anyway, I think we should probably stop here. So that's the thing with the cryptic species, right? They look identical. It's not like this where they look different. But when you look at the genetic divergence, they're clearly 2 separate clades. All right, I think I will stop here. What else do I have? All this is not. Okay, I'll stop with this last slide. Species, a figment of human imagination? Is it? Yes. Again, we are going back to what is a species and all that. Remember, in biology, the only thing definite is the individual organism. Everything above that, there's a continuum. However, we have to classify them, right? And when we are doing that using only morphological character, and our minds are very biased, that's why we come up with wonderful trees like this, because we can't be apes. We are so special, right? But evolution does not care about our definitions. It's doing its own thing, right? But we still need to delimit these species. So the best way out is to use multiple lines of evidence. But remember, species are not a static entity. They are constantly evolving. So what has diverged now, tomorrow if there is selection for them to come together, they'll come together, right? All right, with that, I'm done. Questions? Are you guys more confused, or it's has clarified certain things? Both. Good. You're a true biologist. That's why biology is challenging and very interesting. Yeah, Navindu. Oh, in this one it is chromosomal fission. So chromosome breakup, and I think at the centromere, I forget, I have to go back and check. But basically, so it's not a duplication event. So the total chromosomal content has not increased. It's just that they have broken down into smaller pieces, and you have more number of chromosomes. Yeah, so you can also have fusion, but this is fission. Yeah. So people, questions? I think we can take a break now, no? Yeah.
Wanted to remark is that this working definition of Kevin requires, we have solved the problem of identifying the species.
Yeah,
There is
somewhat.
one or other way we can identify, and we
Yeah.
all know what is the species when we are talking about.
Yeah.
But still, the large picture of the process of species
Yeah.
still remains. That's what I want to say.
First, you have to define what is that you are trying to understand, right? So, once you have your entities, then you can study the process of speciation. So, this is the first step. Yeah, so yeah, I'm not going to be discussing about the process of speciation per se, but I think, yes, we should be looking at the process. We should not just say species are static entities and stop at that. They're constantly evolving. Questions, people? So I guess we'll take a break, and then the next session I will show you some examples from the lab where we have actually used these tools to delimit species. Okay. All right. So let's take a break.